All right, so we're in the middle of chapter 3. We're talking about Newton's laws and forces. And there's one force in particular that I think we need to stop and learn a little bit more about, go into a little more detail, and that is the force of gravity. So we've seen that F equals ma, but we learned last chapter that the acceleration of gravity is a equals g equals negative 9.8 meters per second squared. Now, that is the acceleration of gravity. That is the rate at which it causes things to accelerate. But the force necessary to cause the acceleration must then be F equals to mg. We know that the acceleration A must be g, so we can go ahead and put that in there. This is the force to cause this acceleration. And I've gone ahead and given it a subscript of g because this is specifically referring to the force of gravity. So whenever we call it mg, that is the force of gravity. So we now know not only does gravity accelerate things, but that acceleration comes from a force. And this is how we can compute how much force is necessary to cause that acceleration. This is also referred to as weight. So sometimes you'll see people write it as F sub W equals mg for weight. And now is a good moment to make a note that mass and weight are different things. They are related, but they are definitely different. There's some subtle differences to point out. So mass is given by the letter m, and it's measured in kilograms. It has to do with how much inertia you have, how hard or difficult it is to accelerate you. That's what mass is. Weight, on the other hand, is defined as a force equal to mass times the acceleration of gravity. So we can see that weight depends on mass, but they are definitely not the same thing. And since weight is a force, it is measured in newtons. Now, the classic example that is used to differentiate these things is that if you go into space, you can be weightless. If you don't have gravity, if gravity is zero, then your weight is zero. Weight is simply the pull of gravity upon you. So if you go into space, you can be weightless. However, you still have mass. You cannot be massless. You can't just go somewhere and lose some mass. It doesn't work that way. In fact, your mass still works the same when you're in space. Mass gives you inertia. It is still difficult to accelerate something with mass in space. It doesn't matter if it's weightless. Mass has to do with causing acceleration. So something with a lot of mass is just as hard to accelerate in space as it is on the surface of the Earth. However, its weight is much greater on the surface of the Earth, and you can be weightless up in space. Weight is when something with mass is in a gravitational field. Mass is something an object has everywhere. All right, well, speaking of that gravitational field, let's look at the universal law of gravitational attraction. So we know how much acceleration is caused by gravity, but we still don't really know why that number is what it is, where that number came from. Well, obviously you could make some observations and measurements and try to come up with it, but it actually falls out of some fundamental equations. So this equation here is the universal law of gravitational attraction. And we're not going to work many problems with this, but I wanted you to be familiar with the existence, at least, of this equation. Now, I have written here F sub g, because this is always going to be gravity. This is the equation that describes the force of gravity. And it's given by a capital G constant times m1, one mass, times m2, another mass, and it's divided by r squared, where r is their separation. And I've given the value for g over here, 6.67 times 10 to the minus 11, and it comes with units of Newton meters squared per kilogram squared. those are units that were picked specifically to cancel with these masses and that radius squared to leave you simply with newtons. All right, but what I really want you to pay attention to in this equation is the 1 over r squared bit. The fact that this is over r squared. That is a theme we will see recur later on in this semester. So don't necessarily need to remember this equation in all of its details, but if there's one thing you remember that it's an inverse square law. What does that inverse square law mean? Well, inverse means inversely proportional. That means that if that r were to go up, if you increase the separation, the force goes down. And the square law means that whatever you do to r, you then square it, and that's the effect on F, your force. So for instance, if you doubled the separation between two objects, you then square that effect. So double means 2. You square 2 to get 4. If you double the separation, you get 1/4 of the force. If instead you were to triple that separation, well, that's like multiplying by 3. We then square 3 to get 9, and we would get 1/9 of the force. And the same is true in the opposite direction as well. If we get these things closer together, well, a smaller r, if r goes down, F goes up. They're inversely proportional. And again, we square whatever happens to the r, and then that is what will happen to the F. So if we were to shrink the distance by a factor of 2, we would multiply the force by 4, and so on. All right, now let's look at just a couple of fun examples of this in action. So let's look at where the acceleration of gravity comes from. How do we know what it is, other than just making a bunch of observations, dropping things repeatedly and measuring their acceleration? Well, we can actually find it using equations. For instance, we know that force is given by ma. We also know that force is g m1 m2 over r squared if we're talking about the gravitational force. So we could make this ma or mg, like this f sub g, equals to this f sub g. Little m, which would call u or any object on the surface of the Earth, that little m's in both sides of the equation, so it cancels. And we're left with the acceleration is big G times the mass of the Earth over the radius of the Earth squared. I went ahead and pulled these numbers and plugged them in. So we have 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth, 6 times 10 to the 24 kilograms. That's a big number. The Earth is quite massive. And then we divide by the radius of the Earth squared, because the separation isn't just between where these two objects touch each other. It's really about the distance between their center of mass. And so the center of the Earth is what we're measuring to. So the center of the Earth to the surface, where you are, 6.4 times 10 to the 6 meters. And that whole thing gets squared, about 6.4 million meters. If you put all those numbers together, plug them into your calculator, you find that acceleration is 9.8, and the units break down to meters per second squared. So we have shown, theoretically, what we should expect the gravity on the surface of the Earth to be. And you can actually use this equation right here to compute the gravity on any planet or moon by plugging in their mass and radius. One last fun example, I usually pick on a couple that flirts too much during class. If we take two people, we can measure the gravitational attraction, the force of attraction, between two people. So take one person at 50 kilograms, another person with a mass of 80 kilograms, and let's say they're about a meter apart, sitting next to each other at a table in a physics classroom. Well, the force of gravity between them was g m1 m2 over r squared. So we plug those numbers in, mass 1 and mass 2, 50 and 80 kilograms respectively, separate them by a meter. We plug it in and we find the force of attraction is 2.7 times 10 to the minus 7 newtons. That is 2.7 10 millionths of a newton. Barely any force. There's very little attraction between these two people in physics class. This is when I usually tell them to go down the hallway. Maybe they can check and see if there's any chemistry between them. But all right, I will leave you guys with that bad joke. We will have one last video in this series. We're going to take a deeper look at net force when we see each other again. So take care. Talk to you soon.